PTP supervision in IP media infrastructures. What should we truly look at? My name's Kevin Salvage. I'm the Sales Engineering and Technical Marketing Manager for Leader Electronics of Europe, based in London in the UK. And if you have any questions concerning this presentation, Leader or Fabrics products, or test and measurement techniques, please don't hesitate to reach out and contact me on the numbers currently displayed on the screen. So whether you work in OBs, studios, remote production, PTP is locked. How many times have we seen this, yet there's issues with the pictures? PTP, the industry's comfort blanket. PTP has become the timing backbone of SMPTE 2110, but the way it's supervised today often gives a false sense of security. Everything indicates PTP is locked, yet pictures tear, audio drifts, or systems collapse the moment something non-ideal happens. How PTP supervision is commonly handled today. Locked/unlocked status. Devices report PTP locked, in sync, or time valid. And basic offset numbers. A single displayed value, like grandmaster to follower offset, plus or minus 200 nanoseconds, or mean path delay. Standards compliance claims. A single displayed value, like SMPTE 2059-2 compliant, or SMPTE profile supported. Why these metrics give false confidence? The problem is that none of these metrics describe behaviour over time or under stress. Locked is binary, reality isn't. Locked just means within some interval threshold. You don't know how close it is to the edge, how often it's relocked, or whether it's quietly hunting or oscillating. Offsets are a snapshot, not the truth. A single offset value hides jitter, wander, asymmetric changes, micro instabilities caused by traffic or path changes. Compliance does not equal performance. A device can be fully standards compliant and still recover slowly from a grandmaster change, mishandle boundary clock behaviour, or fall apart under packet delay variation. The uncomfortable truth. PTP supervisors in broadcast is often designed to reassure operators, not to protect live output. And that's why PTP has become the industry's comfort blanket, warm, familiar, and very reassuring, right up until it isn't. And what actually breaks IP media timing? The real enemies of PTP stability: phase lock versus timing errors. Phase lock is when a device says it is PTP locked. It usually means it has selected a grandmaster, its local clock is frequency locked, that the phase lock loop is stable, and it is following the grandmaster without jumping or unlocking events. In other words, the clock is stable and tracking. This is often shown as locked, PTP OK, or synced. But phase lock alone tells you nothing about how accurate the lock is. And that's where timing errors come in. Timing error is the actual offset between the follower clock and the grandmaster. It's usually expressed in nanoseconds, and it's defined in IEEE 1588 and SMPTE ST 2059 as the difference between the expected and actual time alignment. In broadcast terms, time error tells you where the video, audio, and ancillary data will line up correctly. A device can be perfectly phase locked, rock solid, reporting no alarms, and still have unacceptable time errors. Practical recommendations? Monitor time errors, not just lock. Trend time errors over time, especially after grandmaster switches. Specify max time error, not just PTP compliant. And be suspicious of WAN PTP. Mixed boundary clocks and transparent clock design, and vendors claiming PTP locked without numbers. What is packet delay variation, or PDV as it's actually known? PDV equals variation in the time it takes a packet to traverse the network, not the average delay. The change in delay from packet to packet. So in PTP, we have sync, follow-up, delay request, and delay response packets are time-stamped. The follower assumes the path delay is stable. Packet variation delay breaks that assumption. So the maths still work, but the answer's wrong. Why PTP really hates packet delay variation? PTP calculates time using small number of packets, not just long statistical averages. That means one badly delayed packet, one queued sync, one microburst can directly translate into time error. This is fundamentally different from SDI, word clock, black and burst, and tri-level sync. Those are continuous and analog in nature. PTP is packet-based and bursty. PTP also has a number of assumptions. The first is that there is no delay between timestamp being created and the packet leaving the interface. But in reality, as we can see here, some PTP network cards can add the timestamp into the original sync message. But in theory, you have what's known as the delay in network stack. So that's from when the message is actually created to when it leaves the interface. So ideally, you want to use a two-step method, which is much more accurate as the timestamp is added to the follow-up message. So this now means that the follower time has a very accurate T1 time because it knows exactly when it left the grandmaster. And so now the follower is incredibly accurate. Path asymmetry. Round trip time is symmetrical. Typically, the delta T2, T1 grandmaster to the follower will be slightly higher than the T4, T3 due to PTP competing with all the video and audio traffic. If this value gets too high, then it can indicate that your network is starting to be slowed down, and you may need to look at the amount of traffic on this leg. So here's a great graphical example. If you have to be in the office at 9 a.m. in the morning, the likelihood is you're going to join a queue of other people who also need to be in the office. So it's going to take you a lot longer. And let's view that as our T2 minus T1 time. However, if you've worked overnight in the office and then are leaving to go home, you're going to get there a lot quicker because there's a lot less traffic. So these are parameters that you need to monitor constantly on your network to ensure the health and performance of your PTP operation. The final assumption is there is no variable delay jitter in the network. I'll leave that one there. I'm not even going to go there. Clocks under stress, the bits we don't watch. Boundary clocks behaving within spec, but poorly. Grandmaster behavior under load, network congestion, or redundancy switching. Silent degradation, systems drifting without anybody noticing. Hybrid reality, where things get messy. SDI, black and burst, tri-level have to live alongside PTP. The simplest way to ensure that your black and burst, tri-level sync, AES and PTP remain synchronized is by having all reference sources generated from the same oscillator, a single oven-controlled internal oscillator that can be locked to an external GPS, house black, or PTP reference signal. That way, if the sync pulse generator loses its GPS reference, both back and burst, tri-level sync, digital audio, and PTP references will use the sync pulse generator's single oven-controlled internal oscillator and go into stay in sync mode. And then, when the external reference returns, a slow sync is used to ensure that no interruptions to the output reference signals occur. And this makes it possible to construct an extremely reliable synchronization system for both IP and SDI infrastructures. So in your hybrid IP and SDI facility, are black and burst and PTP the best of friends? Or are they always fighting? And the most common conflict we see in hybrid IP and SDI facilities is what's known as a reference mismatch. So let's take a look at what a reference mismatch is and how we overcome it. Here we have a very traditional system with two sync pulse generators, leader LT4670s, that generate all of your traditional SDI reference signals along with PTP and an emergency changeover unit, the LT4448. So in a correctly operating system, all of the reference signals are coming from the primary LT4670. But should a failure occur, for example, say the GPS reference is lost, this will cause the best master clock algorithm to select the backup LT4670 as the grandmaster. But in the meantime, the emergency changeover unit is still providing the SDI references via the primary LT4670. And that reference mismatch can be catastrophic within a hybrid IP and SDI broadcast facility. Because although many devices within that are IP, they actually have a black and burst reference input. And the reason for that is that they are internally processing in SDI. So they're taking that 2110 signal, they're de-encapsulating it, they're processing it, then encapsulating it to put it back out. And the smallest of difference between black and burst and PTP can have catastrophic quality of service implications on your operation. So to overcome this, Leader has added the sync alignment cable. So this overcomes a reference mismatch, whether it be PTP or black and burst failure. The new LC2187 LTC and failover cable is connected directly to the two LT4670s and the emergency changeover unit. So let's take a look at this in operation. So here we have our system with the primary LT4670 as both the grandmaster and the reference generator for all of the SDI infrastructure. Our failure occurs again, so we lose our GPS reference and the best master clock algorithm switches so that the backup becomes the grandmaster. Now we have our reference mismatch scenario. So with the new leader sync align cable, also we've upgraded the software on the LT4670s. So they now feature the ability to monitor the best master clock algorithm. And should a change take place, we can now force an error on one of the black outputs. And this will cause the emergency changeover unit to switch. So now we have all our reference sources coming from the bottom LT4670. So that's one failover scenario. But we have probably the more traditional scenario that you're familiar with, that basically we lose a black and burst. So this results in all of my SDI references switching to the backup LT4670. So to overcome this, we've added the ability to monitor the changeover unit status using the best master clock algorithm. So now, when that failure to black occurs, we adjust the priority 1 setting so that the backup LT4670 now becomes the grandmaster. And this results in all of our reference sources coming from the bottom LT4670. And these transitions happen seamlessly, so there is no quality of service issue or interruptions to your references, which can affect your live production. We also have the ability to manually reset these, because unlike in the telco world, where we want to self-heal, we want to do this manually. And once we've carried out the necessary service to the top LT4670, we can hit a changeover reset. And this will now reset so that the SDI references come from the top unit. And we can also recover priority 1, which now resets that to its original value, so that now PTP returns to its top LT4670. So these are really useful and essential if you're running in a true hybrid IP and SDI facility. Supervising PTP without drowning in data. Where should you monitor PTP? Should you actually monitor it at the PTP distribution layer? Or maybe you're going to monitor it on your spine switches. Or are you going to monitor it on your leaf switches? Or, as most people do, is they monitor it at the endpoints. But as you can see, PTP issues can be introduced anywhere across the network. So with tools like the Fabrics SX tag IP, we can connect the tag directly to the PTP distribution layer switch. We can connect it to any of the spines, or we can connect it to the leaf. We can basically plug straight into the network and monitor the health of PTP. Is it the grandmaster you're expecting to see? Are the priority settings correct? Is the switch both frequency and phase locked? Who needs what? Broadcast engineers versus operation versus network engineers. You all need something different. And across the Leader and Fabrics product range, we have a suite of tools that will monitor the particular parameters you require. We have a comprehensive range of parameters displayed from PTP domain, grandmaster ID, priority status, clock class, clock accuracy, clock source, PTP time, and also the video timing and system timing of your video, your audio, and your ancillary data, along with the first packet time, margin, and RTP offset. And we can also monitor the status and messaging, which again is vital. Don't just take it for granted that a switch says that its PTP is 2059-2 compliant. Go in there and check. Make sure that you're not getting timeouts that are causing quality of service issues. The Leader, LV56 and 7600, feature traditional crosshair timing display graphs that any engineer who's familiar with SDI video will know and love. And here we have the PTP to black and burst phase. We can also have PTP to RTP phase and PTP to first packet time phase, allowing you quick and instantaneous view of what is happening now on your network. And also, we have tools that will display all of the information around PTP, which port is locked, which port is ready, a wealth of information. But the problem is that none of these metrics describe behavior over time. And that's where the Leader Zen series supports a graphical display that allows you to see graphs such as your delay time, your offset time, and your PTP to RTP times for video, audio, and ancillary data. And these graphs can be scaled anywhere from 2 minutes up to 72 hours. And they can also be exported as a CSV file for analysis if more detailed investigation is required. And on the Leader Zen series, you can also customize the display layout. So you can align different measurement tools. So here at the top, we have the inter-packet arrival. Then we have our path delay and our PTP timing. So now you can look and see when you had an interruption or some kind of quality of service issue, you can go back and look at the time when that happened and look at the graph. Was it on the network? Was it PTP? Did I lose either my red or blue network? It makes fault finding so much easier. So here we've seen practical examples of how we can catch failures before they show up as issues on air. So remember, PTP present does not equal PTP fit for purpose. Compliance is not the same as resilience, and supervision must reflect broadcast risk, not protocol theory. If you only look for lock, you'll only find failure when it's too late.